Hello, Mr. Sorrentino here again with another one of the videos for the Math 31 course, and this one's going to be on 4.2 graphing polynomial functions. So we talked about some of the features of a polynomial function in the previous section 4.1. Really not enough though to help us graph it. Because graphing, it takes you to know specifically where certain things are going to occur, and until we get the idea of what to look for, it makes it a little bit more difficult to graph them accurately along the way. So we're going to just find a procedure here that there's certain things that we need to find, and those things will help us determine not only what points to determine what the graph looks like, but also how to scale our graphs and things of that nature as well. So one of the first pieces of information that they go into is that they tell you if you have a polynomial function of degree n, and basically that polynomial function will have at most n zeros. We talked about that in the previous video. If it's a degree 3 polynomial, I would expect to have 3 zeros. If I have a degree 8 polynomial, I should expect to have 8 zeros. Some of them might count more than once. Some of them might be non-real, so we'll talk about as we move on a little bit later into this chapter, and they won't be represented on the graph. But it's important to know that that's how many I would expect to see. We start talking more about the turning points, which are known as critical points in our textbooks, particularly in calculus, which are basically your maximum or minimum. It's basically where the graph kind of tops out and goes back down again, or bottoms out and comes back up. It may not be the lowest or highest point of the graph, because there might be other places where the graph goes higher, but it is represent where these things turn. And so if I have a degree n polynomial, I would expect to see at least n, or I would expect at most n minus 1 turning points. So again, if I have a degree 5 polynomial, I would expect to see as many as 4 places where the graph goes from increasing to decreasing, or vice versa. Those are also important to assist you in graphing as well, because we mentioned before the end behavior could help us with that, because it'll let us know if we see enough of the picture in front of us. But also, once we determine that, from the end behavior that I'm seeing what's going on, if I'm not seeing what I would think would be enough turning points, then I have to consider that there might be something else going on as well, or I'm not looking at enough of the graph, or I'm not setting up a good graphing region to see everything. So that becomes important along the way as well. So when you graph a polynomial function, the following is the procedure that we're going to tend to focus our attention on to do it. So in order to graph a polynomial function, we first want to determine the end behavior like we did in the previous one. That says 3-1. It should really say 4-1. I don't know why it says 3-1. Something I'm going to have to fix in the actual notes. Luckily, I'm doing this before the start of the course, so then I can actually fix it, and you'll have the correct version of it when you hopefully are going through this. The next is to find the zeros of the function. This can be somewhat daunting, and we haven't by this point talked about all the ways of doing this yet. So we're going to start off with some ways where we could use some factoring, and the factoring is pretty obvious, but as we move into this chapter some more, we're going to deal with circumstances where the factoring is not as obvious, and we may have to use other methods to determine how to find these zeros. We want to use the x-intercepts to divide the axis into segments, and then use substitution to determine if the graph will be above or below the x-axis. And I'll show what that means momentarily. We want to find f of 0, the y-intercept, and that's pretty easy, because all the x's will become 0, and you're left with a constant term. Find additional function values to determine shape. That's kind of vague, but once you do those previous steps, you should have an idea of which values of x you might want to explore a bit more and find their values, so that you have a good enough set of points to graph. And I want to be aware of the number of turning points to expect and the multiplicity of zeros along the way. These are things I have to consider as I work through this. So let's apply these to an example now. So we're asked here to draw a graph of the polynomial function f of x equals negative x cubed plus 2x squared plus 4x minus 8. So I'm going to go through the list that we just established in the previous part of this video and come up with needed things to help me graph this thing. So first of all, I want to talk about the end behavior. The end behavior comes from me knowing the degree of the polynomial and the leading coefficient. So I know it's a degree n, or degree 3, which is odd. And I know that the leading coefficient is negative 1, and that's less than 0. So having an odd degree means that the two ends should point in opposite directions. Having the leading coefficient be negative 1 means that the end behavior should look more along the lines of this. So I know what the end behavior is going to look like. So overall, the graph is going to end with the left side pointing up and the right side pointing down. Now I want to find the zeros of the function. The zeros of the function could be a little bit problematic because of the fact that there's different techniques we can use to find this, but they're all going to revolve around some factoring first, because we don't have a set formula to handle degree 3, degree 4, degree 5, so forth and so on polynomials. We have methods of solving linear functions. We have methods of solving quadratic functions. What I'm ultimately going to be needing to do with anything over degree 3 and over is finding a way of factoring it down into linear and quadratic functions or expressions so that I can handle those using methods we've learned in previous chapters. So when I look at the function f of x, and I'm going to work with it over here, if I'm looking for zeros, I'm going to set the function equal to 0. Which, is one of the methods we tend to most often use with a factoring method. So, because I like to get this set into factors where I could determine that, okay, with these being factors of this polynomial, I can, have this as a multiplication of factors, and by the zero product property say, well, if this product equals 0, then one of the parts of this product also has to equal 0. Now, when I look at this, we don't have like specific techniques for factoring, cubic functions. We had, some methods of factoring. Some of them you learned in the high school level math you may have taken. I talked about the AC method of factoring quadratics before. We have those for quadratics, but not necessarily these. So sometimes you have to, look at them and have practiced these enough in order to find out some of these things. But one of the things that I notice about the function f of x is that it does have 4 separate terms. Negative x cubed, 2x squared, 4x, and negative 8. Those are all the terms of this polynomial function. Anytime I have an even number of terms, I can attempt group and factor, which is something we did use when we were talking about using when we were doing the AC method. We eventually split up the middle term into 2 separate terms so that we had 4 terms and could use grouping and factoring. So I'm going to attempt that. If you attempt grouping and factoring with polynomial functions, it may or may not work. If it doesn't work, that doesn't mean that there may not be anything you can find. You just might have to use another method. But this one's going to work for us. So luckily, we have that. As we go into other functions and other parts of this chapter, we'll look at other methods of doing that. I'm going to look to see what I can factor out of each one of these groups. Out of the first group, I can factor out an x squared, and more importantly, I'm going to factor out a negative x squared. I always like to have my leading coefficient or my highest power of x in any quantity be positive. So I'm going to factor out a negative x squared, which means inside the parenthesis I'm going to end up with a positive x, and I'm going to end up with a minus 2. When I factor the second group, some things I'm looking to have happen. One, I want to factor something out of both terms. And two, I'd like to have that quantity of x minus 2 happen again. And it happens to work here. If I factor out a positive 4, I do end up with x minus 2 in here. Because 4 times x is 4x. 4 times negative 2 is a minus 8. And so what I have here is I can factor out the x minus 2, and I'm left with negative x squared plus 4 equaling 0. So now I have this factored into quadratics and linears, and by the zero product property, either x minus 2 has to be 0, or negative x squared plus 4 has to equal 0. The x minus 2 equaling 0 is an easy one to solve. I add 2 to both sides, x is going to equal 2. So x equals 2 is a 0 of this polynomial. Negative x squared plus 4, if I subtract 4 from both sides, multiply both sides by negative 1, and then square root both sides, I get that x is going to be plus or minus 2, which boils down to this saying x equals 2 or x equals 4, or x equals negative 2, sorry. So some important things happen here. When I went through the solution process, you notice that the x equals 2 showed up twice. This means that x equals 2 is a 0, but it has a multiplicity of 2. Whereas x equals negative 2 is the other 0. So I know I have coordinates 2, 0 and negative 2, 0. Notice I am not graphing anything yet, because I have to first figure out other things about this particular function and know how far to scale it. So I'm not like immediately putting these numbers in yet, but these are numbers, I'll put some stars next to them, that I'm going to eventually want to plot. Now, when you get to step 3, we have these x-intercepts. We want to be able to divide the x-axis into segments and then use substitution to determine if the graph will be above or below the x-axis. So I'm going to call this test above below. And as we get into some other things eventually that we can actually find with polynomial functions, some of these can get replaced or streamlined together with something else. So I'm just going to set up a little number line here just to kind of keep track of where the x-intercepts are. We have negative 2 and we have 2. And much as I did before, and now I know these are zeros. I want to get an idea if the graph is above or below the x-axis based on what numbers I plug into this. So for instance, between these two numbers, the number 0 would be between them. I want to know, okay, between -2 and 2, is the graph above the x-axis or below the x-axis? So if I do f of 0, I'd work that out and get that it's a -8. Pretty simple to use because of the fact, and this is also part of the next step, we do want to find the y-intercept. So as I said, some of these things you're being listed here, you can kind of kill two birds with one stone in some of them. So I know that f of 0 is equal to -8, which means that 0, -8 is also another point on the graph that I'm going to plot. Knowing that f of 0 is -8, that tells me that at 0, I'm below the x-axis. So between -2 and 2, I'm below the x-axis. When I put in 2, and I do f of 2, no, f of 2 would be 0. So if I pick another number that would be in this region, let's say 3, f of 3, well, I'd put that in my calculator and compute it. And when I do that, I get a -5. Which means that after the 2, so between -2 and 2, I'm going to say it's below the x-axis. After 2, it's still going to be below the x-axis because f of 3 is -5. And if I pick a value to the left of -2, say -3, and I do f of -3, and put that in my calculator, I get 25, which means it's above the x-axis. The cool thing about doing this is also has given me additional points that are on the graph, because this indicates here that I have a point at 3, -5. This indicates that I have a point at -3, +25. So that has given me the points on the graph. So with this information, I might actually have enough to plot this. Let's see what it looks like and determine if we need any more numbers. So as I graph this, I'm going to use the blue. I'm going to go a little thicker on this. Now, so far, I know I had to fit at least up to 25. So if I scale my graph, which is going to be something I want to do first and foremost, I want to scale my graph. It looks like, since a lot of the stuff that's going on here is happening between -3 and 3, if I go by ones on my x-axis, that looks like it's going to be good enough. So 1, 2, 3, 4, make -10. I already have a y value appearing in an ordered pair of 25. So I might want to make it go a little bit beyond that. I mean, because I don't know where the maximums and minimums are going to be, yet. But I at least want to go up to 25 at this point. So maybe go up to 30. So maybe let each one of these, let's let each digit be 5. So this is, so you have to be able to do some of this stuff on your own without the use of the calculator, aside from using it maybe as a computational tool. So, plotting some of the points that I do have at this point. I have this 0, -8. And I'm going to have to judge where that is. I mean, I would say it's roughly about here. I have the two zeros. I have 2, 0 and -2, 0. So 2, 0, -2, 0. I have the point 3, -5. So 3, -5 would be right here. And I have -3, 25. So -3, 25 would be right here. Based on what I'm seeing with the graph so far, it looks like it's going to do something along the lines of this. Which certainly does account for the multiplicity of 0. or the multiplicity of 2 at 2, 0, because it's touching the x-axis but not passing through. Looks like I do have like a lowest point around that 0, -8. So I have an idea what the shape looks like. Maybe I want to find an additional point over here so that I'm being more accurate, because I mean, at least I had a point over here that I can say, okay, that left-hand side's doing that. I know I'm seeing enough of the graph because the end behavior is behaving like it's supposed to. The left-hand side's pointing up, the right-hand side's pointing down. I have all three zeros represented because the multiplicity of 2 means that one of them counted twice, so I do have 3 zeros here. I do have what looks like 2 turning points shown here, and I should have that many for this. So really the only other point I might want to have is maybe find out what's going on at 5, or somewhere in that neighborhood. So maybe doing one more and do f of 5 to see what we end up with. And when I do that, I get -63, which indicates, well, that's going to be a point at 5, -63. Which kind of falls off where my graph is. I mean, I would probably have to guess that -63 would be somewhere like right at the edge of what I could show you here. Maybe then I'd say, okay, well, let's just try to see what happens at 4. So at least I have one other point to go with. So if I do the same calculation at 4, I get -24, which means I have the point 4, -24. And so I can plot that point now here and say, okay, 4, -24 would be roughly about here. And so now when I want to graph this, I can say, okay, it's probably looking at something along the lines of this. And then remember, I want to be as accurate as possible, but I'm not plotting as many points. But notice how the end behavior worked its way in here, knowing some factoring worked its way in here, determining parts that are above or below the x-axis worked its way in here. And generally that's what the graph looks like. To verify at this point, I could show you what it looks like on the calculator. And since I have a good idea of the window I've used on this, I can make a very similar window on my graphing calculator. So let me pull that up. And now, knowing that I set up a window here for my graphing window that goes from -10 to 10 on the x's, -10, 10, and I went by ones. I let my y's go from -50 to 50, and every 2 spots I went was 10. So that means that my scaling, I went by 5s. In reality, I could also make it go by 10s as well. And so when I graph the function, and by the way, I noticed that, and I fixed it, I've done some editing. When I go back to my y equals, originally I did not have the plus sign right here. I've since corrected that. So now when I graph it, it should look like this one. And as you now see, the only difference is, like here, I could see that 0, -8 I kind of looked at as being the minimum, whereas the minimum looks like it's a little bit lower than that. So, but overall the graph is pretty accurate. So, so that's good enough. And as we go into more techniques of dealing with the function and finding things about the function, we'll be able to produce even more points for the graph along the way. So we'll certainly make it even more accurate as we go along and find other things about it. Which brings us into another theorem that has its uses. We don't use it very specifically. We kind of use the concept of it as we go through other parts of this polynomial graphing process, but it is kind of important for us to mention it and talk about what it says. So let's have a look at it. The theorem is known as the intermediate value theorem. It's helpful in some ways when you're trying to think about, finding points on the graph, and it kind of relates to that above and below test that we were doing beforehand. But the intermediate value theorem says this: given any polynomial p of x with real coefficients, so we're talking about that all the numbers in front of the x squares are real numbers, in that A and B are real numbers, so A is less than B. If P of A and P of B have opposite signs, then there is at least one real value C that's between the two, and the polynomial is 0 at that value. It basically is telling me that, if I put in a value in a function and get a positive number, and like go up maybe just go up one unit and say, okay, if I have like f of 1 is like 4 and f of 2 is -3, that means that somewhere between those two numbers, the graph has to pass through the x-axis, and therefore it has to have at least one spot where it has a 0. So this is kind of a roundabout way of locating zeros and doing it kind of more of a graphical way. As I said, we don't use it directly, but keeping the idea behind it helps us realize, okay, well, I know if I'm above the x-axis here and I'm below the x-axis there, then I have to pass through it somewhere, okay? So this could also be helpful for us finding it. So for instance, if I'm looking at example 2, it wants to know, is there a real 0 between x equals 1 and x equals 2 for this function? So the only way I'm going to be able to do that is to actually calculate those out. So let's calculate f of 1 and f of 2. So I calculated these two values out. And what I see here is at f of 1 I was at -4, at f of 2 I was at positive 51. There's a sign change. And that allows me to say there is at least one real 0 of f of x between x equals 1 and x equals 2. It doesn't tell us what that 0 is. It doesn't tell me if there's even more than one 0 between them, which could be a possibility. It just means that I should be focusing my attention on that region of the graph to see that I should at least be able to find a 0 there, maybe more. And I could also need to find out a way of determining what the value of that 0 is. When I look at B, same question, different function, or same function too. Is there a real 0 between 3 and 4? So I still have the same function. I'm going to rewrite it for our purposes here. I'm going to do f of 3. I do f of 4. So for this, I have no sign change. Theorem. If I have a sign change, that means I have at least one 0. If I have no sign change, all I can really say is it's inconclusive. I could say there's no evidence, but I cannot say no. I don't have evidence that there is one, but that doesn't mean there may not be one. And the reason why it's important to note that is because maybe I picked two numbers that are too far apart. Maybe what happens with the graph between 3 and 4, although having a big number for f of 3 and an even bigger number for f of 4, it's less likely. But say at 3, it was up here, but it may have went through, came back up, and I'd be up to here when I go back to f of 4. There could have been a lot of stuff that goes on between those two numbers. So, I could actually have 2 zeros or 3 zeros, but there's no sign change to let me know, okay, to look for one. So that's why the intermediate value theorem, it has a use, and like kind of thinking about like one way of locating zeros. And it is a premise that the calculator uses when finding zeros, the method we've shown before, because that's why I had to pick an x min and an x max, or you're right bound, you're left bound and right bound, because I wanted to pick values close enough together that I would get a sign change, still get a sign change, and that'll help me locate where the zero would be. But if I have two values where I have two places or more where the graph crosses the x-axis, I could fail this test, but still in fact have zeros. I just don't have the evidence to say one way or the other. So that's the issue with the intermediate value theorem, because the intermediate value theorem either allows you to say definitively, yes, there's at least one zero, or I don't know. That's it. You cannot say a definite no. You can point to other things and say, okay, if I would talk about end behavior and other things, work into it, I could probably throw out the possibility that there's another zero there. But I'd have to have other information, and the intermediate value theorem itself would not tell me for sure if there was a no to that question. And so that brings me to the end of 4.2's video. If you have any questions regarding this concept or anything else we've covered so far, please make sure to come to my office hours or bring them up in class. Until I see you in one of those locations, or until the next video, I will see you around. Have a good day.